This is level 2 of the CFA program, the topic on quantitative methods, and the learning module on basics of multiple regression and underlying assumptions. You might be tempted to skim over this learning module because of the word basics in there, but I caution you not to. Although this module is relatively short and relatively basic, there are a handful of items that we're going to need as we extend through the next 6 learning modules. I'm guessing you figured out that the CFA Institute has moved to this learning module presentation, and I think it's an awesome evolution by the Institute. It's good news for you candidates out there because it tends to condense material into shorter kinds of chapters. They're calling them modules. And it allows for a greater linkage between and among the different modules inside of a topic. Now, you guys who've watched me over the years, hopefully it hadn't been that long, but you'll note that I try to steer away from identifying LOSs that are more important than others. I try to give you some hints in there because some of these LOSs, it's almost impossible to ask an exam question. But I'm going to go ahead and break my kind of a rule here. And so I want you to look at these 3 LOSs. I mean, the first one is pretty basic. The second one we learned back in level 1 for just a simple linear regression model. And in fact, I got out my old materials. And when I went through the program, 100 years ago, simple linear regression wasn't even a part of level 1. So this is an extension, a logical extension of what we do in level 1, from simple linear regression to multiple linear regression. So all of the material that you learned within the last year applies. But this third LOS, I'm going to go ahead and say that this is the most important of the 3 for the sole reason that the end of module vignette has 5 questions in it, and every question asks you to interpret the residual plots. So pay close attention as we go through the slide deck on the graphs. What we're going to do is take LOS 1 and LOS 2 and try to figure out what they mean in terms of looking at a graphical representation of the data. All right, so what I want you to do is I want you to take a look at this multiple regression model. You see a plus sign in there, and just visually eliminate the second plus sign and everything that's over on the right. This is what shows up in level 1. That's a simple linear regression in which we're saying something like, we have 2 variables. One we think does a really good job of explaining the other one. So we talked about this in level 1. There's a dependent variable, and then there is an independent variable over on the right-hand side of the equal sign. But now all we're doing is we're just adding extra independent variables over on the right-hand side. So we still have the dependent variable that's noted as y, and then there's an intercept term, lowercase b, and then there are all these slope coefficients. And those are, and this is important, in level 1, we just probably called them slope coefficients, but now they're partial slope coefficients because what they do is they tell us the relationship between that independent variable and the dependent variable holding all of the other independent variables constant. That's important. And remember to interpret those as partial slope coefficients. And so there's x1 and x2 and x3 and x10 and x50 and x100. You could have as many as you want over there. And we'll talk about this as we go through the next 6 learning modules about, is there an optimal number of independent variables? And the answer is probably no, but based on all the material that we cover in the CFA program, you could probably reasonably determine how many is how about nearly optimal. I'm pretty sure that's not a calculus term or a finance term, nearly optimal, but you get my point. And then all the way at the end, there's something called an error term or a disturbance term, and that's going to be really important, especially when we do some graphing here. So what are we saying? We're just saying there are a handful of variables that can be used to explain some other variable out there. All right, so what are we doing here? Look in the horizontal axis, there's an x variable. And on the vertical axis, there's a y variable. So there's the intercept term right there. And then there's the slope coefficient, just like it was back in level 1. We're going to do, what did you learn back in grade school or high school? Rise over the run for the slope coefficient. That just means changes in one intercept as it relates to changes in the, I'm sorry, did I say intercept? Changes in one axis over changes in the other axis. And notice that we have drawn a blue line. So one of the things that we're assuming in here under multiple and simple linear regression is that these variables have linear relationship. I'm not sure that second arrow point is really important, but boy, the Institute could slip that in there for one of these exams. Intercept term defined as the value of the dependent variable when all of the independent variables are 0. So you think about a model. Suppose you're trying to predict something like, oh, what's critical in 2022? How about inflation? So we're trying to predict inflation, and so we have a whole bunch of variables on the right-hand side, like, oh, I don't know, Fed policy, federal funds rate, maybe yield to maturity on AAA rated bonds, or what's the likelihood of all of those things being 0? And probably not very high. So my professors in college, I don't know that we ever even talked about the intercept term as being important. All right, why are we using this multiple regression? Well, I said this in my introduction here. Test existing theories like, oh, these variables here, like currency values and interest rates, they're probably super important in explaining changes in inflation. I like that second one, identify relationships between variables, because on the economic surface, we may find that currency values and inflation are related. But there might be some hidden relationships, maybe a latent relationship that we don't obviously see, and regression analysis can help uncover those relationships. And then, of course, we can use multiple regression to forecast inflation in the future. Look at that second embedded bullet point. Due to their complexity, statistical tests and fundamental justification are necessary to explain financial and economic relations fully. Boy, that sounds like a mouthful there, but I'm going to go ahead and rewrite that sentence in saying something like, look, the Institute is teaching us all sorts of stuff about the relationships between and among variables, and so let's just go ahead and use all of this material to make a reasonable justification for performing a statistical test. I mean, clearly the Institute is not going to have a question on the exam that says something like, okay, Jim holds the CFA designation and he's trying to predict the returns on Twitter after, the attempted takeover, and then the poison pill, and then all the politics involved, and then all the stuff that's going on with Twitter. And what Jim's going to do is he's going to use everything that he learned in the CFA program, and he's going to come up with a model that says, hey, the returns to Twitter are a function of the number of clouds out in the sky on a daily basis and the number of foul shots that LeBron James makes during the course of that day. I mean, that makes absolutely no sense at all. So economic justification, that's super important. All right, so what the reading does is give us some kind of examples, and that's what we do here in the purple and in the red. So we can do profitability, we can do growth, we can do revenue, we can do dividends, we can do all sorts of stuff. And we can come up with some kind of a model that predicts either financial difficulties or financial success. What we can also do is we can say something like, let's look at stock price, let's look at trading volume, and let's see if there's correlations between and among other kinds of variables. But maybe some analyst is trying to determine how do they change daily? Why is it that Twitter has this much volume before the whole Elon Musk stuff, and now it has this much trading volume? Yeah, those are really great questions. All right, let's go ahead and look at an example. Here we go. Impact of inflation and real rates on the price of the US dollar. So look on the left-hand side of the equal sign. There's our dependent variable, the price of a US dollar index, whatever that is. And it's probably a basket of exchange rates between the US dollar and, maybe 5 or 8 or 10 or 20 different currencies out there. So you have this basket index. And so what do we think as a good financial analyst? We think that inflation is probably important. We also think that the real interest rate is important. So there's our multiple regression model. So what do we have to do? Well, we need to, whoops, I didn't mean to go ahead. We need to go out and collect data on the price of the US dollar index. We need to collect data on inflation and collect data on the real rate of interest. And so in an ideal world, what we would do is we would have this data readily available to us, and let's just say on a daily basis. So we could go back over the last, let's just pick a number of days, 100 trading days, and get these two independent variables and the dependent variable. We could get that data for the last 100 days. The problem in reality is that while we could get the price of the US dollar every day, it'd be difficult to come up with inflation because the government doesn't announce rates of inflation on a daily basis. It does it on a monthly basis. Now, the real rate of interest, we might be able to back into that using things like, maybe treasury securities and maybe inflation rates that are predicted by some kind of a model. But then you get into the problem of, okay, what are the problems with the model? So you see my point here is that we need to make sure that when we're collecting all this data that we have data points that refer to same time trends. So what we'll probably do here in this model is, since we can get actual inflation from the government on a monthly basis, maybe we'll just get monthly prices and monthly real rates of interest. So let's suppose we do all that and we perform a regression analysis. So there are the coefficients going down the left-hand side, 81, a minus 276, and a positive 902. So what does that tell us? That there's a negative relationship between inflation and the price of the dollar. There's a positive relationship between real rates and the price of a dollar. And then the next column is some measure of standard error. You should remember this back from level 1, standard error. In almost any kind of phrase or term that has the word standard in it, like a standard deviation and a standard error and a standard error of the estimate. I mean, they have individual different kinds of meanings, but they essentially tell us, what's our degree of error? How wrong are we? If we have a data set that looks like this, and here's the mean somewhere in there, and the data set goes way, 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 way out to here, well, then we'll probably have a high, some kind of a measure of standardization. But then that's important on that third column. There's the test statistic and there's the p-value. So you can use either one of those to determine significance. So what did I say earlier in that second column? That there is a negative relationship and a positive relationship, inflation and real interest rates. But we need to ask ourselves the question, do we care? So maybe they go up and down together, but is it material? How about that? Now, of course, we can't use that term here. In our quantitative methods terminology, we need to use the term, are they statistically material? We call that statistically significant. And so you should remember from level 1 that it's probably an okay general rule of thumb to think of a good a t-statistic that's significant if it's greater than 2. My professors in college, they allowed us to get away with that in just kind of general terms when we were reporting our data to them, whether we were doing papers or writing our dissertations. But then they said, to do the real test, you need to make sure you get out the tables and do the t-test or the z-test. And so that's how p-value comes into play. So what do we say? The test statistic for inflation is a minus 1.18 and its p-value is 27. So that is not statistically significant. So all we can do is say that partial coefficient of a minus 276, we can say with confidence that there's a negative relationship, but that it is not statistically significant. But then look at real interest rates. We have a p-value of 0.01 and a test statistic of 322. So wow, that sounds an awful lot like this is statistically significant. That partial coefficient is statistically significant. And so, what's the standard? The standard is a p-value of less than 5%. And that's if we want 95% confidence. I mean, we could say we want 97.5% confidence or 99% confidence, or we could say something crazy like we want 50% confidence. I'm not sure if that would be anything reasonable, but we could say that. So there's that last sentence down there. The only the real interest rate variable is significant at the 5% level. There we go. Oh, here's some more summary data on what I was talking about there in that previous slide. All right, so let's move on to the next one here. Possible drivers of a company's percentage return on capital. So we take profit margin, we take sales, and we take the debt ratio as possible drivers. All right, so what are we doing? 5% level of significance, sample size of 25. Oh, that's important. So that's less than 30. So we're going to use a t-value. Back here, what did we know? We were not told how many we collected, did we? We could probably figure it out, but. So let's quickly go through that. Notice all these are positive, right? They're the standard errors. There's the t-stat, the intercept term. That is statistically significant, but that only just tells you that the line doesn't go through 0. And this is probably why my professors said, let's not worry about the intercept term. Although there was one example that we did about trying to determine if the risk-free rate of interest, which remember shows up on the vertical axis in the capital market line, is that significantly different from 0? That was probably an okay one. But anyway, what do we have? 1.7 and 1.3. So that's 9%, 0.09 p-value, 0.17 p-value. So sales and debt ratio are clearly not statistically significant, but profit margin is. And so that should make perfect sense. Notice the p-value over there of 0. And there's that far right column comparing the p-value to 5%. All right, how about the LOS regarding the assumptions? And these are the exact same assumptions that show up in simple linear regression, but they have a little bit more meaning because now we have a couple of more variables to worry about. So first one, relationship is linear, right? Independent variables are not random. No definite linear relationship between 2 or more independent variables. If you have that, this is called multicollinearity. Here's the example that I give my students whenever we run into this. Let's suppose that you were trying to determine whether or not your newly installed air conditioner in your house is working. And it's working efficiently. And so you say, all right, I'm going to collect data on the number of times that my air conditioner machine outside clicks on during the course of a day. And to my independent variables are going to be, I'm going to put a thermometer on the roof that faces east, and I'm going to put a thermometer on my roof outside that faces west, and I'm going to put a thermometer out in the middle of my backyard. And so those are my three independent variables. So clearly they're not independent because the sun is going to shine here, and then it's going to shine here, and it's going to shine there. Now there might be some shading involved in there, so there'll be variability. They're not going to be the exact same temperatures, but clearly when the sun is shining and it's 100 degrees outside, those 3 thermometers, they're going to have a high degree of correlation. Expected value of the error term is equal to 0. This simply means that we know that we're going to make mistakes in our model. Let me go back here to this. Let's just go back here to this model. We know we're going to make mistakes in sales and debt ratio and profit margin. It's not going to, those 3 independent variables are not going to perfectly predict the percentage return on capital, right? So we're going to make some mistakes. So the expected value of the error term simply means that the mistakes that we make on this side offset the mistakes that we make on this side. Expected value of the error term is equal to 0. Now, we also need to concern ourselves about the variance of the error term. So it has a mean of 0, but it's not going to have a standard deviation or a variance of 0 because we're going to make mistakes, right? We're making mistakes this way and we're making mistakes this way. That's why we square those differences to get rid of the negatives so that the mistakes on this side don't exactly offset the mistakes on that side. So what we want is that across all those observations, we want that variance of the error term to be equal. This is called error terms that are homoscedastic. Violations of that mean heteroscedastic. Error term is uncorrelated across all observations, which means that, well, let's go back to my silly air conditioner example. I mean, clearly we're going to make mistakes, but how are we going to make the mistakes? The mistakes are going to be made, and those mistakes are all going to be related, because when the thermometer on the front roof makes a mistake, the thermometer on the back roof and the thermometer out in the backyard, they're probably going to make the mistakes. They probably won't be identical mistakes, but they're going to be related. And then finally, we want that error term to be normally distributed, and that's kind of a summary assumption based on the 3 above diamond points. Now, this is what I was saying earlier in my introduction, that if you look at that vignette at the end of this learning module, there are 5 questions, and every question asks you to interpret a graph. And so that's what we're going to do over the next handful of slides. So after we're done this slide deck, I want you to immediately open up your book or get it on your phone digitally, and I want you to look at that final question, that question set there. And hopefully after what we're doing here today, you'll be able to answer those questions correctly. All right, so let's go through a couple of these assumptions. So we need to ask ourselves the question, is the relationship linear? Because it might not be. So the way we do that is that we plot the residuals going up the vertical axis versus the fitted values going along the horizontal axis. And what did we say just a moment ago? Those residuals, that error term, they should have an expected value of 0. So notice there's a 0 going up the vertical axis. And so notice that what we're doing is that we kind of draw a line. There's the red line. That's not really a line, but you can draw something. What the module does is in the graphs in there, it draws a perfect straight line from 0 all the way out through the end of the horizontal axis. Here we kind of just try to draw a red line. It's kind of close to 0. So in order to determine linearity, what you can do is you can look at this graph and you can ask yourself the question, okay, suppose that you were walking along 0. So here, can I do that? I can't even do that with my fingers. All right, we're walking along 0, right? And if we look to the left, we're going to see a bunch of data points. And if we look to the right, we're going to see a bunch of data points. Do we see the same number of data points? And are they about the same distance? So this is really just a regular old, let's go ahead and eyeball it. And this one here, we could probably say, yeah, this is probably a linear relationship because, well, look up at the top. We say there's no pattern evident. So the Institute is very likely to throw a graph at you and say, okay, is this linear or not? Then you just eyeball it and say, you know what, it probably is. But suppose they give you something like this. Oh boy, there's no way that this thing is linear because, there's a little, what does that look like, a mountain? Boy, dare I even say it looks almost like the part of a normal distribution. And so this is nonlinear. So I'm guessing the Institute, when asking this question, would give you something that's relatively obvious. I mean, here, this is linear and this is not. If it gives you a graph that looks kind of like in between these, it doesn't have a total hump, it has just a little hill, I would probably err on the side of nonlinearity. All right, how about the second assumption here, autocorrelation? And so what we're concerned about here is that the error terms are related to each other. Now, this particular learning module mentions this just in passing, but we put together this slide because there's learning module, I can't remember if it's learning module 4 or 5, in quantitative methods, where we're going to take a look at all of these issues, that all these violations of the assumptions, and then how to correct for them and what their consequences are. So this is probably not too terribly important slide other than the definition for this particular learning outcome statement, but it will become super important when we get to that future module. So remember this, autocorrelation. We check for it using the Durbin Watson statistics, and without getting into too many details, once again, we'll do this here in another recording shortly. It's a standard statistic, so all of the values are going to be between 0 and 4, and sometimes there's no autocorrelation. That's, you want the mean between 0 and 2, so that's Durbin Watson statistic of 2. That's a good thing. If it's less than 2, then you have positive correlation. If it's greater than 2, then you have negative correlation. And there's some other tests that we'll talk about here. How about this one here? This is really good. Seasonal or correlated patterns. Go way back up to the very top. Autocorrelation is most often appears in time series models, and that's going to be a super fun discussion that we have, but that's not today. This is what I was talking about with my thermometers on my roof and in my backyard. Roofs? Do I have roofs or roofs? I'm not sure what the plural is of that. So multicollinearity. So here we go. We have an x1 variable and an x2 variable. And so clearly, if that's thermometer 1 and that's thermometer 2, well, there's going to be a high level of correlation between those two variables. Now, notice on the left-hand side, we have this VIF factor. And what that's going to do is that's going to allow us to determine the degree of multicollinearity. And although these relationships are not described in this particular learning module, they are once again in a future learning module. And so just think about this. If this factor is less than 4, there's probably not too concerned about multicollinearity. If it's greater than 10 and you got serious issues, I'm certain that my temperature example would have a factor greater than 10. But then this future learning module says something like, hey, if you're between 5 and 10, then you need to further investigate. What's the point here? The point is to be able to look at a graph here like this and say, oh yes, when x2 increases, x1 increases, and it does it in a linear fashion. That's clearly a violation of this multicollinearity assumption. Now, heteroscedasticity is the opposite of homoscedasticity, in which we said that we want, what did I say earlier? I think I went like this. We want a constant variance. So if we take a look at this same plot, residuals on vertical, fitted values on the horizontal, what do we want? We would like to see those things go like this, right? Just like this. Imagine all the blue goes just like this, like a rectangle, right? But now what's happening here? It goes way out into a funnel shape. So this is a clear picture of heteroscedasticity, where we start out with, very low errors, very low variability. But then as we move out through those fitted values, boy, our mistakes become bigger and bigger and bigger. And so it's a non-constant variance. Look at the bottom there. There are a couple or a handful of tests that we can do to further test for heteroscedasticity and then correct for heteroscedasticity. But that will come up in a new learning module. All right. So once again, what we're going to do is exactly what we did back in that previous example, right? Look at the red line Is that a line? Kind of a curve. I don't know what it is. It's not quite a line. It's not quite a curve, but it's almost linear. How about if I say nearly linear? So that pretty much looks like what we want. Again, pretend that you're walking along that red path and you want to look to your left and you want to look to your right. And if you see the same number and the same distance, then that's probably evidence that the model is correctly specified, at least as the homoscedastic assumption applies. But if we walk along that line and notice early on, we see a bunch of those things, they're pretty close to us. And then as we move further and further, they get further and further distance away from us. And we're upward sloping as well. This is a really cool test. This normal QQ test, what we're doing is we're testing quantiles versus quantiles. And notice that there's a line, right? There's a line up there. So what you do is you go ahead and plot this. And those are circles right there. So those are quantiles. And the quantiles can be almost anything. I mean, they could be 10%, they could be 30%, whatever they are. And so what you want in a perfectly normal distribution, you'd have all of those circles going right along that line from beginning all the way to end. That would be perfectly normal distribution. Here in this example, boy, we're perfectly linear, right? All the way until we get to some point, and so they kind of squiggly away from the black line. But this is a good example of a normal distribution. And so what you'll look for on this picture on the exam. And I think there's a really good example here at the end of the learning module. Excuse me. You'll want to look for something like a smile, where it begins above the black line and it goes on the black line, maybe a little bit below and then back above. So it looks like a smile, right? Or a frown. If you see a smile or a frown, then you're going to see evidence of skewness and evidence of kurtosis. Oh, wow. So normal distribution. Remember, there's no skew, there's no kurtosis. And so this normal QQ plot goes a long way in determining that normal distribution. And remember, this is the normal distribution of the error terms. That's important there. So here's an example of, is that a smile? I don't know. It's kind of a smile, but think about it. That those circles, that path can go down and below and up. If you get one that looks like this, I don't even know what that would look like. But clearly that's a distribution that is not normally. All right, so here's a list of the main assumptions: homoscedasticity, independence of the variables and of the error terms, normality, and linearity. And that takes us through these learning outcome statements. So what have we done? We've really just built on what we learned in simple linear regression. We've added a couple of important things, but then I think the important thing is those interpret the residual plots. You can only interpret the residual plots if you know LOS1 and LOS2. So that should be your focus. Hey, thanks for watching. Have a great day and good luck studying.